afternoon, everyone. Welcome to our webinar, Exploring Natural Hydrogen Plate Type Models from a Development Perspective. I'm your host, Arnes Biogradlia. And let me just say, if you thought webinars were all boring slides and muted microphones, buckle up, because today we're diving headfirst into a topic hotter than Elon Musk's latest X tweet. Yes, we're talking about natural hydrogen, the underdog of the energy world. Joining us today is none other than Dr. Arnout Everts, a geoscientist and energy consultant with more credentials than a LinkedIn influencer. He spent over 33 years cracking the code of global energy resources, and today he's here to share his insights. Think of him as the Gandalf of geology, leading us through the mines of Moria. Except instead of Balrogs, we're facing confusing energy charts and decarbonization targets. Arnout, welcome.
Thank you very much. And thanks for the opportunity to present on your forum. I'm looking forward to a good show. I'll do my best.
It's our honor. And on that note, here's what we're talking about today. Hydrogen supply, what we need to know. The all-important topic of rates and long-term commitments basically define the relationship talk of hydrogen world. Plate types of natural hydrogen. And don't worry, it's not a video game, but it's just as exciting if you're into rocks and gas. Case studies from places like Mali, France, and Spain, because who doesn't like some international intrigue? And finally, how all of this fits into our plans to save the planet. No pressure though. We'll wrap it up with Q&A session. So get your questions ready. And remember, there's no such thing as a dumb question, except for, is this webinar recorded? Because yes, it always is. Okay, let's get into it. Natural hydrogen is having a moment right now. Everyone's talking about it, and why wouldn't they? It's clean, it's abundant, and unlike me after holiday buffet, it doesn't leave a massive carbon footprint. But here's the kicker. It's not just about finding the hydrogen. It's about finding the right kind of hydrogen in the right places. And that, my friends, is where it all gets interesting. But before we start, important announcement. Soon, and you'll be notified about that, we'll have a masterclass on this topic with Dr. Everts, where we'll go much deeper in detail. So all of you interested, be sure to subscribe, since we're going to email that one soon. Now, to help us make sense of this all, I'm going to pass the mic to Dr. Everts. Arnout, please enlighten us.
Yeah. Okay, let me share my screen. Yeah. Okay, the entire screen. Yes. Okay. Put it in slide view. All right. Good day, good evening, good morning, everyone. I mean, for me, it's evening. I mean, in Kuala Lumpur. What I'll run through today is an extended version of a presentation that I gave in November at the EAGE-GET 2024 conference in Rotterdam with the same title. But here, since I have more time here and I hopefully a good audience, I'd like to basically go into a bit more detail and show some of the science behind the summary that I presented in Rotterdam. Okay, the outline of what I want to talk through is so I'll give a brief introduction beyond what Arnes already explained. So I'll go I'll explain a bit about resource classification fundamentals to explain basically what it takes to basically bring a resource to value. I'll talk about hydrogen demand, how much hydrogen do we need to produce for it to become commercially interesting. I'll talk about how important it is to get good production rate and also to be able to sustain these rates for a considerable amount of time. How important this is when it comes to commercialization of a gas, and hydrogen is a gas. And then, so once I've set the scene there, then I'll go into the details of the different play types, and I'll give examples of the different kind of broad play types that I've recognized. So I'll talk about a play type which I call focus areas of natural seepage. I'll talk about coal bed hydrogen, and I'll talk about reservoir-trap-seal configurations, which are kind of like a hydrogen gas field. And then I'll end with a summary, and then I'll do my best to answer any questions that you guys have. Okay, a little bit about myself, so that you basically understand where it is I'm coming from with regards to natural hydrogen. So I'm a geoscientist by background. I have a long working history of working in the oil and gas industry, mostly on developments rather than exploration. And so I've worked with big operators like Shell, Petronas, and then I set up a consultancy, which we grew quite nicely over the years. And then I stayed on as an advisor for a while, and now I'm consulting through my private consultancy vehicle, which is called EAGE-GET. And a lot of the work I've done, especially in recent years, is on what people call techno-commercial due diligence. So look at basically that's trying to translate subsurface resource amounts to value. And this also basically is resource and reserve assessments. I've looked at a lot of projects. Over the last couple of years, I've kind of shifted focus a bit from conventional oil and gas towards energy transition, so geothermal, CO2 storage, and I'm very interested in the prospects of natural hydrogen. But my background as a development geologist is really looking at this. Okay, now what can we exploit this commercially? What would it take for discoveries to basically mature on the resource ladder and eventually become commercial? So, as just a broad introduction, I guess all of the audience will have noticed that there's a lot of interest in natural hydrogen, and that's because hydrogen is seen as a key element of the energy transition, a clean source of energy. And recent finds like the ones in Mali and in eastern France and Albania have received a lot of media attention. A lot of the research and publications to date, they appear to focus on the exploration angle of it. So, and very conceptually, like subsurface sources and fluxes of hydrogen, how much, at what rates does hydrogen get generated in the subsurface, what could be replenishment rates, and then what could be the total amounts of hydrogen potentially trapped in the subsurface. There was a very interesting paper by the US Geological Survey very recently that came out on this. Now, like I explained before, is my focus is a bit different. In this paper, I like to talk mostly about the development potential of different natural hydrogen plays. So rather than talking about subsurface sources, fluxes, and all this, I'd like to say, okay, now let's assume we find a hydrogen accumulation. What can we do with it? So therefore, to determine what we can do with it, we need to consider things like pressure and phase of the hydrogen in the subsurface, reservoir quality, how much resource per unit area do we have in a find? What will be the drive mechanisms and indicative recovery efficiency? And I'll explain some of these terms. What exactly I mean with drive mechanism, I'll explain this later on. What will be potential well production rates? And can these production rates, can they meet the requirements of existing industrial facilities and also potential new hydrogen offtake opportunities that might evolve as basically energy transition progresses? All right, so let me start with a bit of a high-level explanation of resource classification to basically make hopefully all the audiences, especially people not so familiar with resources and reserves and valuation of subsurface resources, to basically bring some of the clarity about some of the terminology, and also make people understand where natural hydrogen, where does this fit in, and where do the discoveries made to date, where do they sit? So in broad sense, subsurface energy resources, including oil and gas, but also things like hydrogen, they fall into three broad groups: what's called prospective resources, and then contingent resources and reserves. Now, prospective resources are they're undiscovered. There may be good indications that they exist, but not all the elements that make up the resource play or prospect have been confirmed yet by drilling. And then there are contingent resources. These are resources. Now, the existence of the resource has been confirmed by drilling, but still the commercialization of the resource is contingent on resolving some of the additional things that you need for basically the resource to become commercial. And this can be basically delineating the size of the resource, but also firming up whether I can produce it at the rates that my buyers need. But it can also be things like firming up commercial arrangements or regulatory requirements, all of this. And then reserves, finally. This term is restricted to resource amounts that are firmly commercial. So either everything is in place for the commercialization to happen, which means that sales contracts are in place, financial commitments to develop the reserve are in place, regulatory approvals are there, or that the thing is actually on production. So when we then think about where the natural hydrogen finds so far sit, then we see most of them sit in the category of prospective resources. These are their amounts of hydrogen that could be there, but we've actually not brought much hydrogen to surface, let alone that we have an idea of how big they are. And now to mature resources across this resource ladder, so to bring something from a prospective resource to a contingent resource and eventually a reserve, you need to do things. So within the prospective resources category, there are things like place, which is like very much a concept. So you have conceptually an idea about hydrogen that could be generated somewhere and could be trapped, but you haven't really delineated areas where they could be trapped. And then you have a thing that's lead, then you have delineated an area, but it's still quite loose. And then a prospect, it's ready to drill. So to mature things from play to lead to prospect, you do exploration studies. I think the natural hydrogen studies that are ongoing right now are very much in this realm, exploration studies. And then to move a prospective resource to a contingent resource, you need to make a drill well and make a discovery. And a discovery means that you prove the presence of hydrogen in the subsurface, and you also bring material amounts of it to surface. And then to now move this to the stage where you can try and think about commercialization, then you need to do things like appraisal, project maturation studies, start working on who can buy this hydrogen, all of this. And then eventually, once you've done this, then you need to start doing engineering studies to figure out what you need to put at surface. You need to firm up sales contracts, approvals, all of this, and only then it becomes a reserve. So there's a long list of steps there that you need to basically go through for a prospective resource to become a contingent resource and eventually a reserve. And I mentioned before that most of the hydrogen discoveries, if you can call them like that, to date, well, they're not even contingent resources yet, and that is because we haven't, with the exception of Mali and maybe Albania, we haven't produced broad material amounts of hydrogen to surface. And even in the case of Mali, this is not a reserve, it's a contingent resource. And the reason for that is that the operator, Hydroma in Mali, they do not sell this hydrogen at commercial prices. And the reason for that is the amount is too small and it's too remote. So it's a contingent resource. Right now, there are no hydrogen reserves anywhere in the world. Now, resource classification schemes used throughout the energy industry are always project-based. Now, what is this project? The project is the link between a resource accumulation and the decision-making and commercialization process. So think of a project, so the resources are in the subsurface, but to bring the resources to value, you need to do a project. So the project is all that you need to do to basically develop the resource, bring it to surface, and then sell it to a buyer. So all the elements that are in there, they form part of the project. And you run the economics to determine whether or not something can commercially work on a project base, not on the resource volume as a whole. This is important. Now, project definition should cover things like field and target reservoirs, well and facility concept, lots of stuff. And obviously, the further you mature a resource and the closer you get to commercialization of a resource, the firmer definition of what a development project should look like or is going to look like must be firm. So for contingent resources, let alone for reserves, the definition of what the project involves. So how much of a resource am I going to develop? What kind of wells am I going to drill? How many wells? Over what type of period? At what rate am I going to supply? All this jazz needs to be firmed up in order for this to be a contingent resource and eventually become a reserve. But even at the exploration stage, people need to consider what the potential project might look like. Otherwise, it's impossible to talk about potential resource value of prospective resources. So some of the discussions I see, and even things basically published in media about basically talking about hydrogen resources, or some people in the media, they even call it reserves. I'm really a bit disturbed by that, because I think this shows that people have no idea how resource maturation works. And really, in order to make this whole discussion about hydrogen and hydrogen commercialization meaningful, we need to start considering what development projects might look like, and who we're going to sell this hydrogen to, and at what quantities. And so this brings me to the next thing, which is who will buy hydrogen? And what volumes of hydrogen do we need to supply to the market in order to satisfy these buyers? So currently, almost all the hydrogen produced in the world, and in 2023, some 90 million ton of hydrogen was produced, and less than 1% of this is green hydrogen. All the rest is gray hydrogen, which comes from natural gas via a process called steam reforming. The vast bulk of this goes to either petroleum refineries and ammonia plants, and then a third off-taker of hydrogen are steel plants. And these fellows, they all require big amounts of hydrogen. A typical petroleum refinery needs 50 tons of hydrogen per year. A steel plant, 70 tons. An ammonia plant, an average size ammonia plant, close to 300,000 tons of hydrogen per year. So these are big amounts. And then, so projects, if we want natural hydrogen projects to basically make a dent into decarbonization of the industry, then we need to somehow look at projects that can supply these kind of these volumes of hydrogen, or tonnages, big tonnages. Now, if if projects can't meet these kind of tonnages, there are other things that we could consider, like a district heating or vehicle fueling hubs, or maybe jet fueling hubs, if you believe that in future there will be hydrogen jets. And these require smaller amounts of hydrogen, but still not insignificant. So a vehicle fueling hub, for example, will typically require about 1,500 tons of hydrogen per year, and a jet fueling hub may need about 30,000 tons of hydrogen per year. So these are still sizable amounts. And now notice that the vertical axis on the graph is logarithmic. And the reason why I use here logarithmic axis will become evident later on when we talk about some of the hydrogen finds to date. If I show it on a linear scale, it looks like this. So now you start appreciating how small these local offtake opportunities are compared to the big industrial opportunities, and especially how much hydrogen ammonia plants require compared to all the rest. But the key takeaway here is that if we want natural hydrogen to play a role in decarbonizing the industry, then we need to supply very, very large amounts of hydrogen. Now, there has been quite a bit of talk about hydrogen for power generation, and I want to address this. And again, it's all about materiality. A large single cycle gas turbine used for power generation, they typically produce 100 to 400 megawatts of electrical power. And if you want to replace this, say a gas turbine, by a natural hydrogen fired facility, then you are talking about a yearly supply of 50,000 to almost 200,000 tons of hydrogen. So a similar amount of hydrogen as what an ammonia plant would need. But obviously ammonia plants, they can't work without hydrogen. For electricity generation, you have other options. You have basically hydroelectric, you have solar, you have wind. So there's other options available for clean energy. So using hydrogen for large scale electricity, so power generation, sounds like a silly thing, doesn't make much sense. And you won't get prices you would get for compared to other applications where there's no other alternative than to use hydrogen. Now, blending hydrogen with natural gas, some people have been talking about this as well. In my opinion, it makes no sense. And the reason is blending hydrogen into natural gas lowers the calorific value. So actually it lowers the heating value. And in terms of lowering the carbon footprint, because the heating value is lower, it almost does nothing. And then power generation on a much smaller scale, then you're talking about competing not with the best gas turbines anymore, but with renewables like wind and solar. And there again, an onshore wind project, for example, typically they have turbine capacity in the 3 to 4 megawatt range. And to match this, you would be looking at supplying hydrogen in the range of 1,000 to 2,000 tons of hydrogen per year. So similar to what you need, for example, for a fueling station. But a fueling station you probably get better prices than to compete with onshore winds. And the reason is that the fueling stations, you have no other option. You need to get hydrogen. But for power, small scale power, there are many other options. So therefore, in summary, I don't think using hydrogen for power generation makes sense. It doesn't make sense on a large scale. It doesn't make sense on a small scale. And you would unlikely fetch the premium price that you might that is associated with other hydrogen applications. Now, when we talk about commercializing hydrogen, or we speculate about what it might take, I think based on the analogy with natural gas, high rates and long-term supply commitments are going to be critical. And let me explain why I say this. Hydrogen utilization projects like conversion of a steel plant to run on hydrogen, or building a green ammonia plant or a hydrogen fueling station, they require large upfront investments with a payback time of many years. And here I give an example. For example, to convert a steel plant that's currently being run on coal with a blast furnace process, to convert this now to a green steel plant running on hydrogen with one of the hydrogen utilization process called hybrid. This basically, it takes a capital expenditure of between 3.5 to 7 billion euros. So a massive amount of money. And obviously it will take many, many years of plant operation to earn back this capex investment. An ammonia plant, typical cost of building a green ammonia plant would be in the order of 600 million to over 1 billion USD. So also a lot of money. And here you see a picture of the world's first small pilot green ammonia plant in Denmark, 5,000 tons. And so this is a very, very small ammonia plant. What you can see here in the background is that these fellows, they have secured their supply of green hydrogen, because you see the wind turbines are in the background. And then a fueling station, typically between 2 to 4 million of USD capex. So a much smaller capex, but then the margins are also much smaller. So again, the payback time will be very considerable. So because we're talking about big capex and long payback time, to minimize project economic risk and exposures, operators of these kind of projects, they will be looking for hydrogen sales contracts with a secure supplier. And with that, I mean a fellow who can deliver hydrogen of the required purity at the required rate, and who can commit supply for many years, typically 7 to 10 years or more, like a good portion of the facility lifespan. So therefore, if we want our natural hydrogen projects to basically compete for this kind of lucrative sales contract, the operators would have to demonstrate to buyers, but also to certifiers, because these kind of to secure a hydrogen sales project, a hydrogen sales contract, there's a whole commercialization process that needs to be followed, and part of it is certification, where independent certifiers go and look at the whole techno-commercial outlook of the project, to validate whether or not what the operator says actually makes sense. And I've done these kind of certifications, so I kind of know a little bit how this is done. So buyers and certifiers would have to be convinced that wells can supply hydrogen at the flow rates required for the industrial facility, that these production rates can be sustained over time, and that commitment, so financial, regulatory, the whole thing, to drill and develop enough hydrogen resources to secure the supply throughout the contract period, so 7 to 10 years or more. I mean, for gas, for large gas projects, sales contracts can be like 20 or 30 years. So you would have to demonstrate commitment. You would have to demonstrate that this hydrogen is actually there. And this is really, really important. Otherwise, you will never, if you have only a small amount of hydrogen and there's a lot of uncertainty, then the operator of the steel plant, he's never going to go and work with you, because if you run out of hydrogen and he's only recovered a small portion of this 7 billion euro that he spent, where is he going to find all the rest of the hydrogen he needs? So that is why high rates, long-term supply commitments, essential. Okay, now that's a bit of the background. Then there's one last bit of background, and then I'll go into the technicalities of the different play types. Here, and this kind of this slide makes the link with the subsurface. I want to explain to the audience here what is reservoir drive and why it is important. So to date, discussions around natural hydrogen, they appear driven by exploration geology. So basically, they're about sources and generation rates, migration pathways, and chance of trapping. So this basically here, this diagram taken from the US Geological Survey is an example of that. So you can see here basically different sources for hydrogen and then some potential trapping configurations. Now, to understand the exploitation potential of natural hydrogen in different settings, we also must consider what recovery mechanisms or reservoir drive may apply to different settings and how effective these are. Now, what's reservoir drive? Reservoir drive is the energy that moves resources in a reservoir towards the wellbore as you remove fluid from the wellbore. And why? What is this? Why is this important? The size of the features that could trap hydrogen, or that basically this where large focused seepage features like hydrogen chimneys around faults and so, these are large. They're much larger than the small size of a wellbore, and that means that most of the hydrogen is actually far away from the wellbore. So to recover material amounts of this hydrogen, there must be something that moves the hydrogen which is away from the wellbore to the wellbore as I flow fluids from the wellbore. And now the energy that does that is called reservoir drive. And in a gas field, like there's this little picture here in the center where I depict basically here a hydrogen accumulation trapped underneath some seal, and this will be hydrogen gas. In a gas field, the expansion of the gas, when you flow the well and you deplete the pressure, gives the drive, and this expansion of gas, because gas is very compressible, this moves basically a resource that is far away from the well to the well. But for some of these diffuse seeps that in hydrogen may play a big role, I struggle a little bit. What would be the drive mechanism there that would make the hydrogen seeping in a diffuse manner far away from a well? What would make this hydrogen flow basically towards a well when I drill a well into one of these seeps? Anyway, parameters that influence the reservoir drive mechanism and effectiveness there's many, but pressure, fluid phase, and reservoir properties are really important. So that is why when I now go and talk about the different hydrogen plate types, I'll talk quite a bit about these different parameters: pressure, fluid phase, reservoir properties, and then from there, drive mechanism. Okay, so conceptually, subsurface hydrogen systems comprise the same key play elements as the petroleum system counterparts, namely source, reservoir, trap, and seal. You must have a source to basically store material amounts of hydrogen in the subsurface. You need a reservoir with storage capacity, and then you need some sort of trapping configuration. And if you want to trap it and make it stay in the subsurface, you need a seal. So considering representation of these play elements, so the different forms that reservoirs and traps and seal may take in different settings, and also considering this recovery or drive mechanisms, I propose that the natural hydrogen finds to date can be broadly grouped into 3 play types. And what are they? The first one is focused areas of natural seepage, where basically there's an active hydrogen source, hydrogen is migrating up, but there's not much trapping. It's just essentially seeping, but since the subsurface is not uniform, the seepage is not uniform either. It's focused into major pathways, and if you drill a well into one of these pathways, you may see hydrogen influx into a well, and where a migration pathway basically reaches surface, you see surface expressions like fairy circles and so. Then the second plate type is coal bed hydrogen, and this is where place where hydrogen is absorbed onto a molecular scale in coals, because coals can absorb a lot of hydrogen. They can absorb a lot of gases, and hydrogen is one of the gases that they can absorb. And then the third plate type are reservoir-trap-seal configurations. So here all the play elements work. In the coal bed hydrogen, I must have a source. I must have coals, and the coal is a reservoir, but I don't need a trap and a seal, because the coal just absorbs and keeps the reservoir, keeps the hydrogen there. But for reservoir-trap-seal configurations, where I trap gaseous hydrogen at excess pressure, like in a conventional gas field, I must have a source, obviously, but I also must have a working reservoir, a trap, and a seal. So let's look at these different play types. So the first play type, as I mentioned, focused areas of natural seepage. So these are settings where I have an active hydrogen source, so expulsion of hydrogen from one or more subsurface sources, but I've limited, if any, trapping of hydrogen in gaseous phase, because my geology may not be so favorable. Either I have no adequate trap, or I may not have an adequate reservoir, or I may not have an adequate seal. So in such situations, like I mentioned before, migration, so hydrogen generated from the sources will migrate upwards because it's very light, so it migrates upwards under buoyancy forces, and this migration is not uniform. It will find migration pathways, which are fault or fracture zones, or laterally extensive permeability thief zones, and it will migrate upwards through these features. And in these features, formation waters, you can expect them to be saturated with aqueous, that means dissolved hydrogen, and there may be small amounts of residual hydrogen gas in these in such migration pathways as well. And the reason why I say small amounts of residual gas is because the so-called critical gas saturation of hydrogen is very low. Hydrogen is a very small molecule. It's extremely volatile, and therefore it starts becoming mobile at very, very low saturations. And the saturation at which bubbles of a gas become mobile and start moving under buoyancy forces, this is called the critical gas saturation. So critical gas saturation of hydrogen, based on lab experiments, is always very low. Some believe it's zero, but the more common belief it's like a few percent, 2-3%, which means that you can't have more than a few percent of residual hydrogen gas in migration pathways, because all the excess gas would move out of the system. Now, where these migration pathways outcrop, I already explained this. You might get surface seeps. If you drill wells through these migration pathways, these wells may see significant hydrogen gas shows, especially if wells are drilled underbalanced. And what is underbalanced? It means that the pressure of the drilling fluid is less than the pressure of the formation, which means that as you drill the well, you apply a little bit of a pressure drawdown on the formation, and modern drilling techniques often do this. And water wells, for example, they're always drilled under balance. So then as you drill through a layer with dissolved hydrogen in it, then you may get gas shows, just because around the well, the pressure, you put a little bit of pressure drawdown. Pressure is a bit lower in the well than it is around the well. Drawing down the pressure to reduce formation water solubility of hydrogen will be the main recovery mechanism applicable to these plays. So that is to say, if you want to produce hydrogen from these focused migration pathways at rates faster than the natural migration, then the only way to achieve this is by drawing down the pressure and making additional hydrogen to basically come out of solution, form gas bubbles, and then basically move up. And that is because hydrogen solubility in water, it increases as a function of pressure. So drawing down the pressure by pumping of water lowers solubility of hydrogen, and it will bring hydrogen out of solution, and then hydrogen bubbles form, and then they come to surface. It's like opening a bottle of mineral water, the same concept. Now, the example of one of these focused hydrogen seepages, where most of the hydrogen is in aqueous, so dissolved form, but where it's moving through permeable layers, potential fracture zones and so. The example I like to discuss here is the Bougou field in Mali, and I think most people who have looked at natural hydrogen will know about this, because this is the world's first and to date only producing hydrogen field. It was discovered in the late 80s by a water well drilled in 87, and a very shallow water well under 12 meters. It was shut in after a gas explosion, and then in 2011 they reopened it. A company called Hydroma, they tested it, and they found it could flow hydrogen at 1,500 cubic meters a day, which is, it sounds like a lot, but actually it's only 135 kilos a day. And in the test rate, that equates to 50 tons of hydrogen per year, which, if you recall the rates that I mentioned earlier on, like in the tens of thousands of tons per year that you need for an industrial facility, is tiny. And then they hooked it up to a local power generation, supplying a nominal 5 tons of hydrogen per year. And the reason exactly why the nominal rate is so much lower than the test rate, I don't know. It's in the publications about Bougou, it's not really clear why that is. But anyway, this is the Bougou one well. And then Hydroma drilled a bunch of appraisal wells in 2018, another 13 boreholes, and they logged them, took some core, and the stated objectives were to delineate the shallow hydrogen accumulation and appraise deeper intervals. And so some further hydrogen shows were found in the shallow layer, but also in deeper layer. But no pressure or flow tests were made. Well, at least they were not disclosed. And to our knowledge, none of these additional wells were brought onto production. Now, this Bougou has been described in media and in a few publications as an accumulation of gaseous hydrogen, a hydrogen gas field. What I will show in the next bunch of slides, based on analysis of all the data I could find in the papers by Hydroma workers, but also combining this with other geological and aquifer information that I could find about Mali, I will present to you why I believe this is basically, it's an aqueous, so it's dissolved hydrogen dissolved in the formation water with potentially a very, very small gas cap at the very top of the structure. So it's not a hydrogen gas field. I'll show it to you, the evidence. So a bit about the geology. So the Bougou wells, they're drilled in a very old intercratonic basin. These are very, very old sediments from the Neoproterozoic. Here we see the log of one of these deeper appraisal wells, Bougou 6, that was drilled all the way into the basement. So we can see what the succession looks like. You see it also on the cross section. The colors here on the cross section, they match with the color bar here in the center. And these greenish shades, these are sediments. And then the purple, these are volcanic sills. So there's a bunch of volcanic rocks that were intruded into this as subhorizontal layers, so-called sills. And here you can see in the well that basically the sedimentary succession, the sedimentary rocks, they consist of sandstones with occasional limestones, and then very shallow up there is a dolomite. And you can see here, towards the right, there is a curve that is annotated here, hydrogen gas logging. And the further that curve deflects to the right, the higher the gas shows. And I've annotated the strength of the gas shows qualitatively here with the color of the circles. So you can see that the shallowest layer, which is a dolomite at around 80 to 100 meters depth. This is the layer that is produced in Bougou 1. And it has by far the strongest gas shows of the whole succession. The gas shows in the deeper, mostly sandstone layers are much weaker. Now, as I mentioned, I believe that even in the shallow layer, the bulk of the hydrogen is not hydrogen gas. This is hydrogen dissolved in the formation water. Let me show you the evidence. We zoom now in on data from this upper layer where the Bougou 1 well was tested. So the first argument that I put forward as to why this cannot be a big accumulation of gaseous hydrogen is when we look at the structure. So here on the left, we see a contour map. So we see a picture from Google Earth in black and white, and we see the different well locations, and we see here colored contour lines. This is a depth contour. These are depth contours of the top of this upper dolomite stringer where the Bougou 1 well is producing hydrogen from. And I made this map based on the information made available in open domain by Hydroma and others. And you can see here the Bougou 1 well with the yellow asterisks. It is near the crest of a northward plunging anticline. So red means shallow depth, and then purple means bigger depth. The relief on this feature from the downflank portion where Bougou 19 and Bougou 20 are to the crest where the Bougou 5s are is about 80 meters. So it's quite a bit of relief. But you can see that the structure, so it's some sort of northward plunging anticline, but there's to the south, there's no obvious closure. And then, but more importantly, there's not much relationship between the strength of the gas shows in the different wells, which is the shade of red to blue. Red means strong gas shows. This gray blue-gray means weak gas shows. You can see there are wells with good gas shows, Bougou 20, Bougou 14, which are like up to 80 meters down the crest. Bougou 1 is near the crest, and the Bougou 5 wells are on the crest. So there's a significant structural relief, but there's no relationship between the strength of gas shows and structural elevation. It's impossible to define a base of show or a hydrogen water contact. If someone were to propose that all the gas shows in all these wells belong to the one and the same hydrogen gas accumulation, then a hydrogen gas accumulation of 80 meters length at this shallow depth would exceed the lithostatic gradient, which means that the excess pressure of this hydrogen would be able to basically lift up the rock at the crest of the structure. So for sure it would breach the fracture gradient. So there's a problem here. There's too much structural relief on this trap, and there's no pattern to the gas shows. It's impossible to define basically a gas accumulation based on this data. And then I talked about pressure. Hydroma didn't disclose pressure data in any of the appraisal wells, but there is pressure data made available in the Bougou 1 well, the producer well. So they report that there's a shut-in tubing head pressure, so that's the pressure measured when the well is not flowing, 60 psi, it's about 4 bar. It's very low. And then there's a flowing tubing head pressure of 34 psi, so that's the pressure when the well is flowing. So that means that they flow the well with 26 psi drawdown. Now I've made here a pressure versus depth graph. So on the horizontal is pressure, on the vertical is depth. So I've drawn in from this 60 psi shut-in tubing head pressure, I've drawn in a hydrogen gas gradient because I think it's reasonable to assume that when the well is shut in, there is gas, hydrogen gas in the upper portion of the well. So that is this gas gradient. And then I've tried to figure out where the aquifer gradient, so the water lag connected to this gas, where it would be based on regional aquifer data. And there's basically there's various publications about aquifer geology and water table depths in this part of Mali. And the reason for that is that water is a very precious resource in a dry country like Mali. So they report that the groundwater table in this area is about 30 meters below surface. So I draw an aquifer gradient starting at 14.7 psi, which is atmospheric, and then I go down. And now you see the problem. It's these gas shows in Bougou 8, which is on the crest. That's the closest one of the closest offset wells to Bougou 1. These gas shows cannot be from a gaseous hydrogen in this reservoir because there's no way I can intersect this gas gradient with this aquifer gradient and have this in the gas. You would have to have a groundwater table which is 30 meters deeper than that, so like 60 meters. But even if you say, okay, maybe in this location the groundwater table is 60 meters, there are other wells like Bougou 20 and Bougou 14 where that are another 60 to 80 meters structurally down from this well. So you'd have to push this groundwater table to like 120, 130 meters. I think it's impossible. So in summary, these low pressures reported in the Bougou 1 well, they're simply incompatible with a gas cap connected to a regional aquifer. Cannot be. These gas shows, they must come from hydrogen that's dissolved in the water lag. You can see here, possibly at the very, very top of the reservoir, there could be a tiny gas cap. And then when we look at the logs, we see a similar story. Hydroma, in the papers they published on Bougou, they show some well panels with different petrophysical logs. So they show the density log, the Newton log, the sonic, and they show it alongside with hydrogen logs, mud gas shows. It's a pity they didn't show the deep resistivity. They must have run it. But anyway, we have what we have. The Newton log, which is shown in blue, it deflects to the far left, which means high Newton porosity, whereas the density log is flat. And in a Newton density cross plot, you see this here on the right, that makes the data plot here to the lower right corner of where it should plot for a dolomite. So that the Newton porosity is higher than you would expect. So that we know from the core that the porosity is between 5 to 10%. And we see that the Newton porosity is higher than that, but the density is low. So the density is consistent with a dolomite with low porosity, but the Newton log readings are not. In the My Guide All paper, this is described as a hydrogen effect without giving any petrophysical explanation. I've looked at this and I've discussed this log signature with quite a number of experienced petrophysicists, and everyone agreed that this log response is exactly the opposite of what you would expect from a rock filled with hydrogen gas. And why is that? Is that the Newton log, it records the so-called hydrogen density, which is the number of hydrogen atoms per volume of rock and fluids the log is exposed to. And a hydrogen gas has a very low count of hydrogen atoms per volume unit because the gas is so light and the molecules are very far apart. So and especially at low pressure, so in a reservoir filled with hydrogen gas, the neutron should deflect sharply to the right low Newton porosity, whereas the density should sharply this is an electron density. This should deflect sharply to the left, showing the low density of the gas pore fill in the pores. Petrophysicists working on gas detection, they call this the butterfly effect. A low pressure hydrogen gas should give a very spectacular butterfly effect. So a low Newton porosity, so the blue curve deflecting to the far right, and the density deflecting to the left. On the Newton density cross plot, it means the data should have plotted to the top left, a gas effect. And we see that the Bougou anomaly is this is consistent with a rock where the pores are filled with water, but where also some of the minerals that form the matrix of the rock, they may have water-bearing minerals, and maybe this is because of hydrothermal alteration. So in summary, the petrophysical expression of the Bougou reservoir also tells you that these mudblock gas shows, they cannot be from a free hydrogen gas. They must be from aqueous dissolved hydrogen in the formation water. Then now, how can we explain hydrogen being produced from a reservoir with hydrogen dissolved in the formation water? Well, the explanation is the pressure drawdown that they apply to the well. This 26 psi pressure drawdown would have halved the solubility of hydrogen. So basically, you apply a 26 psi drawdown, it halves the solubility of hydrogen. So hydrogen comes out of solution from the formation water. It forms bubbles and then it flows into the well. And you can work out, given the thickness and properties of this dolomite stringer, that depletion within a radius of about 110 meters would explain the 1500 cubic meters of hydrogen produced in the one-day test. And similarly, 5 tons of hydrogen per year, this pressure sink around the well would have slowly grown to about 700 meters. And I believe that given how continuous this dolomite stringer is, this is very reasonable. Okay, let me speed up a little bit. So how much hydrogen is in this system? I run some numbers here. So for the top layer where the Bougou 1 well is producing from is here, and then the deeper layers are here. So how do I compute hydrogen volumes here? I express it as a resource density because I don't know the size of the trap. Resource density means resource per unit area, and this is typically a typical usage in resource plays like also CBM, shale gas. People use resource density, so that's also what I'm using here. So I'm computing resource density based on the net thickness, porosity, because the porosity, the water with dissolved hydrogen in it is contained within the porosity of the pore space of the rock. Then there's pressure and temperature, which determine hydrogen solubility. And then so I can work out based on pressure and temperature hydrogen solubility. I assume the formation waters are saturated with hydrogen. So then it gives me hydrogen per ton per unit area. And I sum this all up. So I get across all these layers, I get about 3,000 tons of hydrogen per square kilometer. And now to make this hydrogen come out, what do I need to do? I need to deplete the pressure. So for my recovery assumptions, I've assumed a 40 psi effective depletion over the whole area of the resource. So this 1 square kilometer of resource. Over this whole 1 square kilometer, I deplete the pressure 40 psi. And then it gives me 6% recovery, 180 ton of hydrogen per square kilometer that I could potentially recover. Now, this 40 psi is a bit of an assumption, but there's some basis for it. Let me explain. At the top of the uppermost layer, this dolomite where Bougou 1 is producing, the pressures are very, very low. Depleting it 40 psi brings you almost to atmospheric. You can't deplete it more than that. The deeper layers, you could deplete it more, but the reservoirs are very tight, and the aquifer might fight back. And also, depleting different layers differently means I need to drill more complex wells with downhole control, or maybe a dedicated wells. The well concept that I have in mind when I run numbers here is the simplest well concept I can think of, which is you would commingle all these layers, so perforate the different layers, have a pump at the bottom, so you produce water with hydrogen via the tubing, and then you also capture hydrogen that's bubbling up via the analysis. Now, at what rate, and so this concept and a 40 psi uniform depletion across all these zones gives me it's consistent with this 180 tons of hydrogen per square kilometer. Now, at what rate could we produce this? So, observed rate from the upper layer, nominal offtake rate 5 ton per annum, flow test 1500 meters per day, or 50 ton per year. Now, arguably, this is from a water well, not optimized for hydrogen production. I've run some numbers, and um, um, I figure that if you assume you reduce the skin from maybe 10, maybe this water well has a skin of 10. I mean, you don't really know, but it's definitely will have a decent skin, and you reduce it to a skin of minus 0.5, which is the lowest you could achieve with a vertical well. Then I reckon you can get about 170 ton per year of hydrogen, and then adding in the deeper zones gives me another nine, basically another 130 tons. So all in all, 300 ton per year. So then we get this picture. You see here, 5 ton nominal from Bougou 1, 50 ton test rate, a speculative 300 ton of hydrogen from a future well, but we are miles away from the industrial facility requirements. Now, let's talk a little bit then about if we were to work this into a project, what would its metrics look like, and what would be the impact of possible hydrogen replenishment? So, number of producer wells that you must drill to achieve a contractual rate of hydrogen supply. So, number of wells divided by is the commitment per year divided by the rate per well per year. And then how much resource area do I need to drill is basically the commitment per year times the number of years divided by the how much recharge I get times the recovery factor. If so, this means that if there's active replenishment, you may get away with developing less area, but you would still, to meet the initial offtake rate, you need to still drill the same number of wells initially. That's because the number of wells has nothing to do with whether or not there is replenishment. So then when we look at what we would have to do to use a Bougou type of play to feed to either petroleum refinery or steel plant, ammonia plant, or to some of these local offtake opportunities. So I've assumed, say, a contractual supply commitment for 7 years. Then you find that for the large industrial takers, you need to develop ridiculous amounts of resource area, and you need to drill enormous amounts of wells. If you, for example, for a steel plant, assuming the Bougou test, the 50 tons per year per well from the Bougou 1 test, you would have to drill 1,400 wells. And then even if my assumptions on what a future optimized well could look like, if these are real, then you're still talking about over 200 wells. So lots of wells, lots of areas. And then these wells also would produce enormous amounts of water. So these 230 wells or 1400 Bougou 1 wells, they would produce over the 7 years a staggering 930 million barrels of water. So that's an enormous, these are enormous amounts of water. By the way, these water production numbers I work out with material balance. So, and then even with the local offtake opportunity, so let's take a fueling station, 1,500 tons per year for 7 years, means I need to develop 60 square kilometers of area, and I need to drill either 30 Bougou 1 wells or 5 multi-zone wells for one fueling station. And these wells will produce 20 million barrels of water. So huge amounts of water and a quite sizable number of wells for a very, very small offtake. I struggle to see how this could ever be commercial. And people, maybe in Mali, people would be happy with this water production, but in other areas where producing a huge amount of aquifer water is not really desired. And this aquifer water would also contain other things, maybe salty, maybe traces of other things in there, like hydrocarbons. Disposing this may be a big problem as well. So in summary, I don't think this kind of play type has a huge potential to be commercial. So let's look at the next play type. Oh, here other examples of focus seep. I think in the interest of time, I'm going to skip this. Let's talk about coal bed hydrogen. So coals can absorb lots of gas. They can absorb it on a molecular scale, and so gases they typically absorb are methane and CO2. That's why you have coal bed methane and mine gas. But they can also absorb hydrogen. And this hydrogen absorption is governed by what people call isotherms. So these isotherms describe how the absorption capacity of gases in coal, how it increases as a function of pressure, and it decreases a little bit with temperature. But the pressure effect is much more profound than the temperature effect. And you can see here on this is a graph of pressure versus gas absorption. You can see that CO2 and methane absorption is much higher than hydrogen absorption, but hydrogen can be absorbed. And then, so if you have a rock that has gases, so hydrogen or maybe a mixture of hydrogen and methane absorbed in it, then how do you get it out? You need to draw down the pressure, and you draw down the pressure by basically pumping of water. And then that drawing down pressure moves you down the isotherm. And you can see that the isotherm only starts kinking at fairly low pressure, which means that you need to draw down the pressure quite a bit. Now, the existence of this coal bed hydrogen play type was brought to my attention by the finds of in Lorraine in eastern France. This is one of the finds that had a lot of media attention, as you can see here, gigantic hydrogen deposit, staggering proportions. So let's see, how big is this? The find was made in an old coal bed methane test well called Folschviller 1. And actually, this well was drilled as part of an EU-sponsored project that looks at the coal bed methane development potential of this old mining district. So a lot of data from this Folschviller 1 has been published in open domain, and it's good. So we can understand quite a bit about where the hydrogen is and what the potential is. So we basically, you see a few logs here, density in red. Low density means this is from coals, and the rest of the density is quite high, which means basically it's not coal, it's all the rocks. And we know from the regional geology, and also we can see this from the gamma ray, that most of this rock is shale, and there's a few sandstones, but the sandstones, they have no porosity. You can see this because the density is high. And these coals, they're between 4 to 30 meters thickness, and they have a gas content of between 7 to 10 cubic meters per ton of coal. And that's not staggering, but it's okay. And the permeability of the coals, also reported from tests that they did in the well, it declines from about 3 milliliter at shallow depths to less than 0.1 milliliter at the base of the well. And this decline with depth is not unusual in CBM. Now, how much hydrogen could there be in this system? So again, I run some numbers, and here I run the numbers as I do in the CBM. So how much gas can be absorbed in this coal is a function of how much coal is there, the density of the coal, the gas content. And the reason why I need the density is because the gas content is expressed in meters cubed per ton. So I need to convert from volume to weight. And then how much of this gas is hydrogen, the hydrogen fraction. So then I work this again into a resource density, so million cubic meters of gas per cubic meters, and then how much of this gas is hydrogen. So all in all, I find across the different layers, I find there's about 900 million cubic meters of gas in all absorbed in all these coals, and of this 900 million cubic meters per square kilometers, about 120 is hydrogen. And then if I take a CBM analog recovery factor of about 50%, then that gives me 450 million cubic meters per square kilometer of gross gas recovery. And of that, 60 would be hydrogen. And that works out to be about 5,500 tons of hydrogen per square kilometer. So this looks actually better than the Bougou. So initially I was excited. Thought, maybe this is better. Indeed, it's not gigantic, but this looks better. But the problem comes when you think about what it will take to develop this. So from CBM analogs, and this is like a coal bed methane, with these kind of coals, thick coals but quite far apart, to deplete the pressure sufficiently to get this 50% recovery, you need well spacing in the order of probably 500 meters. So that means that I've basically 4 wells per square kilometer. And then I also need dedicated wells per seam, 1 well per seam. So that gives me 1 well per seam, 4 wells per seam per square kilometer. So 6 seams. So all in all, 24 wells per square kilometer. And I need that because otherwise I can't deplete the pressure effectively enough, and I won't get to this 50%. It also takes too long. And then, so what does this tell me about the ultimate recovery per well? So about 90, so I get 450 divided by 24 is about 20 million cubic meters of gross gas, of which about 2.5 or 226 ton is hydrogen. And then what rates, assuming basically this, I produce this 226 ton over 3 years plateau, with a 3 years plateau, and 50% of the ultimate recovery is on plateau, and this is again typical CBM metrics. This works out to be about 8,500 cubic meters per day of gross gas, of about 300,000 cubic feet per day. Now that's typical CBM. And of that 1.2, so 1,200 cubic meters per day, or 103 kilos per day, 40 ton per year would be hydrogen. So actually the individual well rates of this would be lower than Bougou 1. So yeah, the resource density is high, but I would have to drill lots and lots of wells to get this out. And these wells would again produce lots of water because I need to lift out the water to deplete the pressure. And then I need to somehow separate the hydrogen from the methane. So in the same graph as before, so we see basically here how the resource density compared to the industrial targets looks okay, but the well rates looks awful, miles away. And then from where I need to be. So then when I look at development metrics, you can see that there's no way I can get anywhere near these the industrial takers. You see, I would be talking about drilling thousands of wells and produce enormous amounts of water to basically get to what the steel plant, for example, would need. But even with the local offtake opportunities, 40 wells for a hydrogen fueling station, and these 40 wells would basically produce 1,000,000 cubic meters of water, quite a bit. So the size of the resource areas that you would need to develop are not unachievable because the resource density is okay, but you need very high well counts. You would produce very big amounts of water. Most of the gas produced would actually be methane. So in fact, this is a project like this would be a called methane development with hydrogen as a byproduct. Whether or not this hydrogen could be a value add or a value erosion depends on whether I can isolate a high purity hydrogen cell stream. And this is going to be difficult. There's a lot of research actually on separating hydrogen from methane is a topic of ongoing research, and it's not straightforward at all, especially at low pressure, and it's going to be very costly. So this also doesn't look great. And then the third and last play type, reservoir-trap-seal play similar to conventional gas. So here I have an active hydrogen source, and I have favorable trapping configuration involving one or more porous and permeable reservoirs. So it's like a conceptual picture. A reservoir with a hydrogen gas cap and then a seal above it. The seal must be a good quality seal that can hold the pressure differential of a column of gaseous hydrogen. So evidence for the existence of gaseous hydrogen in place like this would have to come from pressure data. Like in conventional gas fields. Pressure data is going to be essential in demonstrating that gaseous hydrogen is present in the reservoir and what the column length is. And then if you find a play like this, then gas expansion would be the main recovery mechanism. So basically you would have the pressure would follow a P over Z trend, and then which means that well rates can be substantial, and as long as there's no strong aquifer, recovery factors can be high. Now, a possible example of this, speculative, because it's not demonstrated conclusively from the well, is this Monzon 1 in the foothills of the Pyrenees. So here, this is again an old well, drilled just south of Pyrenees in a tilted fault block. So here you see the tilted fault block. This is the well, Monzon 1. And there were gas shows reported as hydrogen gas, were reported from the Bunter sandstein underneath a very thick succession of evaporites and shells. So here I see, there's a reservoir, there's a good seal, and there's potential, and there's apparently a source, if this is indeed hydrogen. So this looks, at least the different play elements are here. But for now, since these are only drilling gas shows that were basically based on the analysis done, this was reported as predominantly hydrogen, but there's some ambiguity about this analysis, and no hydrogen gas samples were brought to surface. So for now, this is speculative, unproven, but worth a further look. and hopefully a test. Now, I take this thing here as an example of what a find of gaseous hydrogen could look like from a development perspective. So here, same philosophy as before. So I run some numbers. So I've 30 meters gas lag with about 10% porosity, 36% water saturation. So it means that 65%, give or 66 is hydrogen. And then here the hydrogen gas expansion factor. So that works. That gives me hydrogen in place resource density of 37,000 tons per square kilometer. And then there's also some hydrogen dissolved in the water lag. So I add this. So all in all, across what gas lag and water lag, I'm talking about 43,000 tons of hydrogen per square kilometers, of which, assuming initial pressure of 5,500 psi and an abandonment pressure of 850 psi, about 35,000 tons per square kilometer could be recoverable. So this is more like it. This looks like it could work if it's there. So assuming 5 years on plateau, 80% of your ultimate recovery on plateau, 1 well per square kilometer, we're talking about 5,500 ton per year per well. So then when we put this on our graph, we can see, yeah, okay, now we're talking in terms of the resource density, we're getting there, and the well rates. Yeah, now we don't need ridiculous amounts of wells to supply to even a big industrial facility. But then I've also, just for comparison, to illustrate how important it is that this hydrogen is there as a gas as opposed to dissolved information water. I've also run the case where I say, okay, this is aqueous hydrogen, so dissolved information water. So now all of it, so all this 55 meters is hydrogen dissolved in the water. So still 10% porosity, pressure and temperature that give me hydrogen solubility. I assume the formation waters are saturated with hydrogen. Then that gives me, instead of 43,000, gives me 6,000 ton of hydrogen per square kilometer. But more importantly, if I assume 100 psi depletion over a 1 kilometer square well drainage area, I get 100 ton of the 6,000 ton per square kilometer hydrogen in place. I get only 100 ton out. So then it doesn't work. And then development metrics. So you can see that to a Monzon success outcome, where I have basically gas in the reservoir there to supply to a steel plant, for example, I need to develop 14 square kilometers, or give or take, of resource, and I would have to drill 12 wells. That looks reasonable. And then these localized offtake opportunities. Yeah, this is basically here. I can, with 1 well, I can supply to a fueling station, and with 6 wells, I can supply to a jet fueling hub. So this secure the supply for 7 years. So this looks more like it. Where say the play type 1, so if it's all dissolved in water, then you can see it doesn't work. I haven't even bothered to run the industrial size applications. I only look at the localized offtake opportunities. 15 wells over 100 square kilometer resource area to supply hydrogen to 1 fueling station, and then these 15 wells would, alongside the hydrogen, these 1,500 tons of hydrogen for 7 years, they would also produce a staggering 120 million barrels of water. Now, what am I going to do with this water? So the play type 1 just doesn't work. Only play type 3 can work. And yeah, this here summarizes then again what I've already discussed, is that basically only the play type 3 can bring you anywhere near the offtake rates that you require for industrial facilities. But I think even the local offtake opportunities, only the play type 3 can really work. The play type 1 and 2 is going to be really, really problematic. So that brings me then to the conclusions. So type 1, which may be relatively common, will be challenging to commercialize because well rates are low, difficult to scale up, high well counts, lots of co-produced water that may create environmental concerns. For this play, I would say the first priority for if people want to study this further should be on flow testing wells to establish whether it's possible to achieve anywhere near commercial flow rates. So there's really, in my opinion, there's no point basically exploring for more of the Bougou 1 or Albania mine type of place. No, what we should do is first try and flow test place like this to see can we flow at commercial rates. The play type 2, so the cobalt hydrogen, these will be very challenging because of the flurry of environmental concerns that surround CBM developments as a whole, water, surface footprint, challenges of hydrogen methane separation. So for this play, the first priority should be on addressing the technical and social environmental project hurdles. So basically the environmental concerns and the hydrogen methane separation. Again, in my opinion, there's no point exploring for more of this. The exploration should be focused towards trying to establish whether this type 3 natural hydrogen gas fields, whether this actually exists. Because these type of plays could potentially lead to commercial projects. And here, the data gathering should include extensive reservoir and fluid data sets, and especially lots of reservoir pressures. I would MDT the hell out of any exploration well I drill, because these pressure gradients is what's going to tell you whether or not hydrogen is in gaseous form or in aqueous form, and it's going to tell you how long hydrogen columns could potentially be, and this is going to be critical. So then with that, yeah, this is the follow-up. I think we talked about this already before. So with that, I'm going to stop the sharing and basically see who's still there.
Yes.
What's there in terms of questions? And
Thank
I'm sorry
you,
it took so long.
Arnout. No, it really was very deep and insightful. And compared to other presentations we had, this is something that will make people think. And really, thank you for this one, because it shows a lot of data that we haven't actually seen and perspectives. So I think this will be interesting in comments in a few days, to read. Okay, let's pause for a moment to digest all that we heard, shall we? But seriously, doesn't this make you wonder why natural hydrogen is not already in all the headlines? Probably because it's not photogenic as Tesla. But okay, now it's time for your questions. Please submit them via comments or DMs. And remember, folks, this is your chance to ask anything. Just don't ask about Arnout's favorite rock. I tried earlier, and it's like asking a parent to pick their favorite child. Impossible. Let's go with the first one. Oh, USGS have calculated Earth's underground reserves contain nearly 6,000 billion tons of hydrogen. Your comments?
Okay, well, I posted quite a lengthy comment on LinkedIn already about this, but I think it's really a pity that the USGS they didn't try to split their estimations, their model into different domains that represent the different type of settings on the Earth's crust. So to me, obvious different domains are sedimentary basins, which is where most of the petroleum resources, actually all of the petroleum resources are found. And sedimentary basins, they are typified by gentle structures, good continuity of reservoir-seal pairs, so therefore a favorable settings for trapping whatever is expelled from the deeper subsurface. So trapping potential is good there. And then on the other hand, you have cratonic shields, where basically there's no sediment coverage, there's just crystalline rocks at surface. There maybe there are more hydrogen fluxes, but trapping is obviously going to be very, very hard to envisage. And then you have oceanic basins where obviously, well, on mid-oceanic reaches, there's a lot of hydrogen that's basically coming out, white smokers and so. Maybe there's some trapping possible there as well. But of course, it will be very, very challenging and costly to exploit this. But you can see, when you start thinking about it like that, you can see why I say it's really a pity that the USGS, they didn't try and run numbers for different environments, because I think it would have given us much more set of more insightful numbers. Now all we have is one number, and when I tried to then scale the number, I said, okay, let's just say the hydrogen fluxes are uniform across all these different domains. Then say about 17% of the Earth's crust is in sedimentary basins. So 70% of this 6 million megatons of hydrogen potentially trapped, then about 950,000 megatons would be in the sedimentary basins, and this 950 megatons equates to about 20 trillion barrels equivalent of oil. Now, all the in-place oil and gas equivalent of all the oil and gas discovered and produced to date, since basically the start of oil and gas production, is about 35 trillion barrels equivalent. So it would be in the same order of magnitude. Well, if that's the case, then I mean, isn't it odd that no one has so far found a single hydrogen gas field in a sedimentary basin to date, even though lots of other non-hydrogen hydrocarbon gases were found. Like there are gas fields which are almost exclusively CO2 or nitrogen, but no hydrogen. So to me, just that simple benchmark shows that Alice's numbers are unfortunately off the reality scale. But in any case, in any way, I think running those numbers, splitting it across different domains would have been much, much, much better. And it's really sad that this wasn't done, but I think it can still be done. So I'm kind of encouraging the USGS to do this and publish an update on the numbers. I think it would be really helpful.
That's a great point. Let's go with the next one. We have Mauricio Cabra. Natural hydrogen possibilities in Eastern Plains. Thank you for the insightful presentation. I'm not sure what he meant, but you maybe can explain.
I don't know.
If not, okay.
I'm encouraging people with basically want to share information with me and get my opinion on data sets they're working on. Please contact me via LinkedIn.
For sure. What do you think about enhanced production via fracturing? Thank you. Mario Alberto Guzman Vega.
It's a good point, a good question. I think definitely some of the settings where we have good chances to find natural hydrogen, they can benefit from stimulation like fracking. But so definitely, Now, what you need in addition to fracturing, you still need a so-called drive mechanism. So if you think about the analogy with shale gas, because quite a lot of people, and I know that in the USGS, for example, in the paper, they sketch the analogy with shale gas. And they say, look at how shale gas exploitation has taken off. And it is true, it has taken off, but the fundamental difference between shale gas and the settings of natural hydrogen so far is that in shale gas, the gas is trapped inside the shale at high pressure. And why is that? It's because it's generated from within the shale. So basically, the organic rich shales, when they are buried, the long chain organic molecules, they break down, and they generate gas. And if the shale is very tight, it has a problem of getting out. But so it's trapped inside the shale at very high pressure. So if I now want to produce from this, what I need to do is overcome the low permeability. And for decades, people knew there was potential of oil and gas in shales, but they had no means to overcome the hurdle of low permeability. Fracking, large scale hydraulic fracking has given us this means to overcome the permeability. But then so the permeability was overcome, and then the high overpressure in the shale gas gives you the drive mechanism that then moves gas over large drainage areas into the well. But if you don't have this high overpressure, then you can frack, which helps you overcome the low permeability. But there's still nothing that moves hydrogen from areas far away into the well, which is why I say the fracking can definitely be something that will help overcome low permeability, but it will only work in settings where we have high pressures to basically help recover hydrogen from areas far away from the well.
Thank you. Next one from Mauricio Cabra. Thank you. Is it possible to later have the presentation? I think we will post it with the article on the website, so you will be able to download. We have Andy Mardinaza. So plate type 3 gives us more economic of geologic hydrogen volume. So in terms of source of geologic hydrogen, they are serpentinization, radiolysis, ferrolysis, primordial hydrogen, overcooked organic matter. Which one of them could generate the largest geologic hydrogen resource?
It's a good question, and I don't know the answer. My gut feel tells me that say the plate type 3 would logically be something that you would chase in sedimentary basins. It may also exist on oceanic crusts, basically in oceanic basins, but yeah, also still in a sedimentary setting. Now, I think that say in terrestrial or shallow marine sedimentary basins, to find serpentinization is going to be hard. So the more logical sources of hydrogen in sedimentary basins would maybe be radiolysis and overcooked organic matter. But there are other, this is where also I'm happy to admit I'm not an exploration geologist. I'm not an expert at hydrogen fluxes and so there are other people, like the people in USGS, for example, who've looked at hydrogen sources and fluxes for a long time. I think they're in a better position to answer these kind of questions, but it's a very good question.
So people from USGS, you heard this. We're expecting you here to talk about this. Next one from Andre. I agree with Arnout that only type 3 traps is worth to explore. However, it seems they are quite rare.
Yeah. But it's not to say that they don't exist. I mean, to me, this Monzon, well, it's the company, I think it's Helios. They're planning to appraise this, let's see. I looked at it in quite some detail. I must say the petrophysics looks unconvincing, but I mean, who knows? Hopefully, look, maybe on some of my LinkedIn and so, I look like a bit like a pessimist, and the glass is half empty rather the glass is half full. But I'm also I can this the natural hydrogen, say for the planet and to achieve our decarbonization targets, it would be great if it works. So let's hope. I think it's definitely worth a try, but the important thing is to have our expectations right and to look for the right things and stop. To me, it's best to press on the pause button when it comes about generating hype about settings which are very, very unlikely to work, like Lorraine or like like the mine in Albania.
I see your points and your view very realistic, and this is probably proven by the fact that nobody still has found, a proper well, and nobody actually has the result that they are trying to get. But there's also a notion that there's a lot of it, but we just need to find a way how to get it. And that also is in line with your opinion. So the next one from LinkedIn user. Thanks for the talk. It sounds like depth, pressure, reservoir quality, rock trap, demonstrable hydrogen source is the logical pathways for hydrogen prospectors with their geologic profiles. Sounds like almost conventional natural exploration. I think a modular processing solution invention will be required, especially in the early days of an exploration endeavor.
Yeah, maybe.
Yeah.
I like. I agree with most of basically what's being listed here. I mean, to me, and maybe some of the companies maybe they're doing this and they're just not releasing the information to the open domain. But I would uh, uh, pressure test the hell out of exploration wells drilled for natural hydrogen, and I would also try and flow test them. So to me, at the end of the day, for natural hydrogen to move up the resource ladder and get closer to commercialization, we must do two things. Is one, we must prove that significant columns of hydrogen as a gas exist in the subsurface, and the only way you can prove this is by taking pressure tests and demonstrating that the data over considerable intervals falls on the gas gradient. This is also common practice in natural gas. I mean, I've done a lot of gas certifications, and pressure data is always essential. The whole thing stands or falls with pressure data. And then the second thing is we must be able to demonstrate to our investors and stakeholders and to eventually to buyers that wells can flow at commercial rates. And the only way in which you can do this is by flow testing. And then probably I can see how, just like for shale gas, is that there will then be a learning curve where it will take time to figure out what kind of well configuration can bring you from a rate that looks like okay, some encouragement from an appraisal well to eventually a commercial producer well, and this will not happen overnight. But to me, like us, and I'm sorry if I sound like a broken record, the first thing is is figure out now, is there gaseous hydrogen in the reservoir, and places where there is, then you can think about the next steps. Because if it's this aqueous hydrogen, so if the bulk of the hydrogen is dissolved in the formation water, and these are just these diffuse seeps, then you're talking about a completely different ball game. And to me, it's never going to work commercially on a large scale. for the reasons I've explained in my presentation.
Thank you. Next one, John Hansen. Hydrogen is insoluble in pure water, Mali case, and can act as a baffle or seal as in Mali. Does that mean that hydrogen and pure water are co-generated? Albania chromite mine.
I mean, to my knowledge, hydrogen is soluble, be it in small quantities in water, and then the higher its solubility increases as a function of pressure, and it decreases as a function of temperature. So, if in fact all the models about hydrogen fluxes and so, they all assume that hydrogen generated in the deep subsurface, that it finds its way to surface via mostly via what people call advection, which is basically flows of in deep aquifers of waters with different soluble contents. So the idea is that hydrogen makes its way from the deep to the shallow, dissolved in information water. So yeah, it is solvable. It's soluble information water, but not in big quantities. And now the Albania chromite mine is a very interesting case. There, so hydrogen is bubbling up there from mine shafts, and there is they estimate that they vent about 200 tons of hydrogen per year from this mine, and the reason why they know this is that they actually, to avoid explosions, they basically pump off gases from the mine. And now where does this hydrogen come from? The paper by Truchet and others, and I've had lengthy discussions. It's a very nice group there in Grenoble, and I very much appreciate what they've done. Their paper also had a lot of good detail. Lovely work by them. They believe there is gaseous hydrogen in some of these fault zones, and I'm not so sure. To me, the more logical explanation is that this hydrogen is generated in fault zones, basically in fracture zones around these faults, where maybe as a result of the mining, water is brought in, and basically rock is brought into contact with water, that a rock that hadn't seen water before, and then the rock there is a serpent. Is basically it's an ophiolite, so it's an iron-rich rock. So then serpentinization starts, and this basically, I believe that in situ serpentinization, but in swarms of fractures around these faults that basically they intersected when they did the mining, that this is generating the hydrogen. But there's also other possibilities, that maybe groundwater around the mine. There's also, I think there's more. The group in Grenoble has more info there, and I think they're working on further publications on that. It's definitely. Oh, I'm hoping for more information there, but I hope that helps answer the question a bit.
Yeah, thank you. And now we are flooded with questions from all the sides, and we are almost 2 hours in, so yeah, we have time. So next question. What do you see as the core limitations in the current exploration mindset for natural hydrogen?
I think it would be good to focus on the place that are most likely to basically result in commercial projects. And so far, what I see is that not all the attention is focused towards places that based on the work I've done, have a huge commercialization potential. So that is where, but maybe, look, I think some of the exploration companies, they're not releasing all the work they're doing to the public. I mean, logically, they wouldn't. So hopefully, some of them are working on the right things, but focusing on play types and working in these play types, trying to work drillable prospects of things that could eventually evolve in a commercial project. This is, I think, where we need a bit more focus than what we have now.
What gaps in our understanding of hydrogen formation processes are most critical to address for achieving commercial discoveries?
Hydrogen generation process. I'm sure there's many gaps there, and to be honest, say my knowledge about the different hydrogen generation processes is I mean, yeah, I know about what the different processes are, but exactly how well we understand these processes, I won't uh, I won't claim that I'm an expert there. I think there's other people that are better placed to answer that question. So where the way I look at natural hydrogen is more like, okay, let's assume that we have a working source, then and we have a drillable prospect. Now, what are the commercialization chances of of this prospect? What are the commercialization chances of different plays? And so that is where kind of my scope of knowledge is. And so I think the question about sources and where our knowledge gaps are there, I really, yeah, I hesitate just speculating there because I think there's better people to answer that.
How can geological data and modeling be better utilized to identify promising natural hydrogen reserves? And you just gave a lot of data, so I think this one is spot on.
I say, well, I look, there's much more data and there's some modeling I've done. Like, for example, I've tried to model what this Bougou well, this Bougou 1 well, what the pressure would look like around the well. I reckon that, say, we can deploy some of the modeling tools and techniques we have available from the oil and gas industry, and we can easily transfer this to natural hydrogen. And some of this modeling work will give us a much clearer insight into how we can exploit different play types and prospects, and what it would yeah, what kind of wells we would need to drill, and at what rates we could hope to produce. So yeah, there I think there's definitely a lot of strides that could be made, and hopefully some of this work is taking off. Again, it may very well be that some of the operators are actually doing this work, and we're just not seeing it.
Yeah, yeah. Final question. Your thoughts on Dr. Vladimir Larin's research?
Oh, the hydritic earth.
Yeah.
Well, if I mean if hydrogen is more plentiful in the deep subsurface, that would be good. The concept that evolves from that, which is basically trying to hunt for these hydrogen migration chimneys. There, the it's an interesting concept. I struggle to see what the drive mechanism would be. So this is again where I think actually doing some modeling, trying to understand now, is is it can you think of a plausible drive mechanism? How much replenishation would you need to have? And therefore, what differential pressures between out the core of the chimney and outside? What kind of fluxes would you need to get meaningful flow rates from a well that you drill through this thing? I think those kind of efforts would give a better perspective on how whether is this a viable concept or not at all.
Arnout, thank you so much for today's session.
You're
This
most welcome.
was awesome. And for all of you guys, remember, we'll have a masterclass with Arnout, and there will be a lot more details and opportunities to ask and talk. So just we'll keep you posted and stay tuned. That's it for today's webinar. I hope you're leaving here with more knowledge about natural hydrogen than you ever thought possible. And maybe, just maybe, a renewed sense of hope for our energy future. On behalf of myself, Dr. Everts, and the entire team behind this event, thank you for joining us, and we wish you all the best in 2025. Go forth, stay curious, and remember, next time someone mentions natural hydrogen, you can nod knowingly and say, "Oh yeah, play types." Have a great day, everyone.